Okay, today we're going to solve a problem. Uh, we're going to find the difference of potential energy when a spring is compressed and then stretched. Uh, we'll be using the potential energy for spring or elasticity equals 1/2 Ks, which is the stiffness, times S squared, which is stretch or compression. And the problem is a spring whose stiffness is 800 newton meters, newtons per meter, has a relaxed length of 0.66 meters. If the length of the spring changes from 0.55 meters to 0.96 meters, what is the change in the potential energy of the spring? First thing you would like to do is draw the spring. The LO is the relaxed length, right? And the KS is the stiffness, right? That's the top spring. And this bottom spring is the same spring, but it has positions on it. We have the relaxed LO position, and we have the compressed L1 position, and we have the stretched L2 position, and we have S1 as representative of the compression and S2 as representative of the stretch, and both those are measured based off of the relaxed length, or in this case the length in the middle, the LO, and you can calculate S1, like you said, the difference between the final and the initial. For S1, it's the difference between the compressed and relaxed, and that's negative 0.11 meters. And for S2, it's the difference between the stretch and the relaxed, and that is 0.30 meters. So you have an S1 and an S2. That's what we drew right there. And here's our formula for the potential energy in a spring. Like we said, it was 1/2 stiffness times the stretch or compression. And we're looking for the change in the potential energy of the spring. So we do the potential energy. Let's see. Yeah, potential energy 2. I have this wrong. This is 2, 1. Okay, I'm sorry. And so it's the potential energy, the final or the stretched potential energy minus the compressed potential energy, and that's 1/2 Ks S squared, and 2, which is the stretched, minus the potential energy 1/2 Ks S1 squared, which is the compression. And you can just, do some algebra. You can have 1/2 the stiffness of the stretched squared minus the compression squared. Here's the math. Make sure your units line up. I like to change my newtons per meter to kilograms times meters per second squared, just so I can keep track of my units. And that's the first part of the equation. And the second part of the equation is our S2 minus S1. And if you do your math and follow your units, you get 31.16 kilograms per meter squared per in your seconds is -2, which would really, if that was in the denominator. And anyways, those units are equal to joules. So the change in potential energy of this spring being compressed and then stretched is 31.16 joules. Let's see if you can see the whole thing. All right.